Instead, we have to use probability for event over a particular interval of time. For that particular reason, we will be not going for discrete event probability, but we will be using probability distribution function, PDF, we call it. And an example of the PDF is shown in the diagram on your right hand side, and the equation for that is shown above, wherein you have the mean and the standard deviation. The PDFs are usually Gaussian distributions, hence they have an uncertainty associated with it, and this uncertainty can be reduced by using Kalman filters or other estimation techniques like particle filter or extended Kalman filter. And Kalman filters can be used for linear conditions when the systems are linear. For example, if a vehicle is moving only in longitudinal direction, only in a straight line, then we can go ahead with a Kalman filter. But if we are going for if the vehicle is taking us turns and it is steering, then we have to go for extended Kalman filter, which takes into consideration non-linearity. So now we'll discuss on Kalman filters, which is crucial for reducing the number of sensors and hence reducing the overall cost of the system, and also improving the measurements from the perception system. So Kalman filter, if you are aware about system modeling or mathematical modeling of mechanical systems or mechatronic systems, if you're familiar with that concept, you will be knowing about state space model. So state space model, and you will be also be aware about observers and estimators. Kalman filter is nothing but a linear quadratic estimator which has an embedded model of the system in it. An example of a state space model is given on the right hand side, where x of k is equal to f of x of k minus 1, b of u, and w, and x is the system state, u is the system control vector, y is the measured output, w is the process noise. These are noises that are there in the system, generated due to system discrepancies in system modeling, and z is the measurement noise. These are the noises that enters the system because of the sensors or any disturbance on the apertures, as we mentioned before. Apertures are, I think, if I didn't mention before, apertures are lens or the antennas that are used for sensing by lidars and cameras, etc. F, B, and C matrices mentioned in the above equation are matrices that define the state of the system, the input parameters. So the Kalman filtering primarily does precise state variable estimation, and it enables tracking of the estimated state variable and its uncertainty. Kalman filter primarily has two processes. It's a two-step process. First, you have the prediction of the state, which is the estimation of the state, and then you update that estimate. You correlate that estimate with the measurement that you receive from the sensors, and you get an and you update that, the correlated result you update to the perception system. Because this is a continuous process, this is an iterative process, it has an iterative nature, it can be used for real-time operations. And the pros of Kalman filter is it's extremely fast, and it removes the measured noise in the measured signal, because, as I mentioned, there's a correlation between the estimated state of the system and the measured state of the system. So, and then you have the cons, which is it is only applicable for linear systems. In order to consider in the filtering that can be used for nonlinear systems, as I mentioned before, are extended Kalman filters and particle filters. Now, for a short demonstration on how sensor fusion works, I will show you an example that is already there in your MATLABs. If you just follow this link, you will understand, you will get the source code for it. And I'll be moving to MATLAB actually, and in order to, so I'll be first showing the website where you'll be getting this. It's pose estimation using asynchronous sensors. So what do you mean by pose? It's the position of the particular system or an object. Here we'll be considering an object that is moving in a circular path with a radius of 8.42 centimeters and at a velocity of around 2.5 meter per second. So this is the example model. So this is again developed by MathWorks. It's an example for illustrating to show you how sensor fusion works. If we run the system, so yeah, I will change the speed to 2.5. The radius of this circular path is 8.42. Run this particular example. Take some time to solve it, so please bear with me. So yeah, as I mentioned, this particular example is related to the pose that includes the position of the system and the orientation of the system. On the left hand side you can see the position of the object, and then the center you can see the orientation. The ground truth, it shows the actual position orientation of the position and orientation of the vehicle or the object that is in motion, and the blue colored and the blue labeled object is the estimate of the object that is in motion. So on the right hand side you can see there are there is a listing of sensors that are being used. Here we have accelerometer, a gyroscope, magnetometer. These three are part of an IMU. All IMUs include accelerometer, gyroscope, and magnetometer. And then the third is the GPS sensor. Here the object is moving at a very slow pace, so we see that there is a deviation between the estimation and the actual position of the vehicle. Yeah, in order to have a better understanding, I think we will increase the speed of the vehicle, of the object that is moving. Yeah, so here there is an object that is traveling a circular path, and then you have an estimation of that object which is obtained by sensor fusion, which is represented by blue. So the red represents the actual position of the object which is moving in a circular path, and blue represents the estimation that is obtained by sensor fusion. So for this particular example, you can see on the left hand side it shows the position. The right hand on the center you see the orientation of the object, and on the right hand side you can see the list of sensors that are being used for estimation and measurement. So here if you observe this particular window, you can see that the orange object, which is the actual object or the ground truth, it is taking a particular path, and then you have the estimated object or the measurement that is taking there is a small deviation between that. But if you observe the orientation, they are perfectly oriented to each other. Now if we just stop using, if we just consider the data from GPS alone by switching off all the other sensors, we see that the estimation starts deviating. You can slowly see that the vertical axis is kind of moving away from the actual ground truth. So the estimation is getting an error. Now I will increase the velocity of the vehicle wherein we can better understand the system. Click on this generate circular trajectory sensor data. So just click on that, right click on it and press open generate circular. Just press on the second option, which is open. And if you click on it, it goes to the circular trajectory generation code. So in that particular code, if you increase the speed of the object that is being tracked, I'm going to increase it to 12, and that's it. And I'm going to run this particular code. So here we see that it is a simulation. It's not actually, there is simulating an object moving. So that's why we are having this code. This code actually generates the simulation path or the trajectory of the vehicle and of the object in motion. And then you have the, so now this script is run, the trajectory script is run. Once that is run, you rerun the pose estimation script. Here you can see that the velocity of the object has increased. So here we see that the error has increased because the velocity has increased, so the error has increased. So first I will just bring back reduce the error by reinitialization. See, once the GPS signal is switched off, the tracking is going it's deviating from the actual estimation. So it has gone somewhere now. So I'll switch on GPS again. So again, it comes back to the actual position, so somewhat closer. There is still an error. That is because I am not fusing the data from magnetometer, gyroscope, and accelerometer. So again, here, if you see the orientation part of it, you see there is a difference between the actual ground truth and the estimated measurements. So in order to in order to correct this orientation error, we can IMU sensors, which include magnetometer, gyroscope, and accelerometer. Now, if you see, the blue or the estimate is tracking better. It is having a better tracking, and the overall error has reduced, and it is tracking the system more. Now, this is again, we can see that the GPS is at 5 hertz. We can also change these frequencies in order to better understand this fusion algorithm. If we go for 1 hertz, that means the GPS signal is being refreshed at a slower rate. You can see that there is again a deviation from the actual position and the tracking position. So you can see that there is a sawtooth pattern that is being observed here. So that is because the reduced refresh rate. Now you can actually use this particular code. It's available online. It's free. If you have license to MATLAB, you can actually have access to this particular code, and you can test out how sensor fusion is working. Here they have actually used inbuilt algorithms and code. You can actually go ahead and try to code yourself your own sensor fusion algorithm using Python or MATLAB itself. So I think everyone might have understood how sensor fusion is improving the results of estimation. Other numerical techniques that are used for multi-model tracking include extended Kalman filter, as I mentioned before, in order to accommodate non-linearity in a system, and particle filter, wherein you can accommodate non-linearity, non-Gaussian nature, and multi-model systems. Uh, Now, the advantages of sensor fusion, why sensor fusion is a crucial part of any autonomous system development, is because it helps increase the quality of data by fusing uncorrelated sensors, increase the reliability of the perception system by reducing the noise, enables estimation of unmeasured states, means, as I mentioned before, states like velocity and position of a particular object cannot be measured usually, but using sensor fusion you can easily measure it by estimation techniques, and then you can increase the coverage area using estimation again, like Kalman filter. And so now we'll conclude how multi-sensor data fusion is a fundamental aspect of assisted driving or autonomous driving. Uh, Here again, many techniques are mathematical, statistical, and probabilistic techniques are available for fusion of sensor data, and there are high-level mathematical algorithms that are developed. For example, Kalman filter, particle filter, and they are widely used techniques. That's why I mentioned them. And then it is easy to program. Unlike so here you have clear identification what are the steps required for developing a particular algorithm. Wherein, as we discussed before, the deep learning approach, you don't have clarity on how the system is performing or what the system is measuring, because it is basically you are mapping a set of inputs to a set of outputs, and the system learns according to mapping that particular set of inputs to the outputs, and it continues to behave in that way. This classical approach requires less computational performance, as I mentioned before, and deep learning techniques, they require high computational powers. And sensor fusion is not only used in why sensor fusion is important for, it's also important for other domains, is because they have been traditionally used for missile navigation, satellite navigation, and missile tracking systems. So it's not just restricted to automotive industry, it has a very bright, wider scope. So if you are familiar with sensor fusion, you can have you have a lot of career options, but then you have to have a very strong fundamental in the mathematical implementations that we discussed. So I just gave you an overview. These are various terminologies that are related to sensor fusion. You can actually go back and read more on it, and you will find that there are a lot of mathematics that are behind these algorithms and these concepts. So I encourage everyone to go back and at least take money, go back and look on to all these points like Kalman filter, particle filter, sensor fusion, Bayesian equation, the Bayesian theory, etc. So here are a few reference books that you can refer for sensor fusion and for localization and perception systems, perception system development. As I mentioned before, sensor fusion is not restricted to one particular domain. It's a multidisciplinary topic. It has applications in a lot of domains like robotics, missile systems and satellite systems, aviation, etc. So these are certain job roles that you can that you might have, like sensor fusion engineer, motion planning engineer, localization systems development engineer, algorithm development engineer, because this particular sensor fusion deals with a lot of mathematics, programming, and algorithm development. Because you have to understand that even if you develop an algorithm, the algorithm must be effective. It should consume less processing power, or it should be effective. I mean, the prospective companies that you can get a job are there is always the OEMs that are available, and then there are tier one companies that are actually spearheading the innovations and research and development in autonomous vehicle development, which include LG Soft. They develop softwares like LG SVL, which is a simulation platform wherein you can simulate autonomous vehicle, means autonomous environments, wherein you have a highly connected highway, and you have multiple vehicles on that highway, and you can simulate those environments, use a different configuration of sensors, infrastructure based sensors or vehicle based sensors, and club and fuse the data between infrastructure based sensors and vehicle based sensors in order to get a better mapping. And other set of companies that use these skills are map developers like Here Maps, and there are other HD map development companies in that support autonomous vehicle development. Yeah, so these are the opportunities.